Hi students, in this lecture I am going to discuss problems based on buoyancy force from Verma. Let us see first one. See the question given. A cylindrical object of outer radius or outer diameter 10 centimeter, height 20 centimeter and density 8000 kg per meter cube is supported by a vertical spring and is a half dipped in water as shown. Find the elongation of the spring in equilibrium condition if the object is slightly depressed and released. Find the time period of resulting oscillations of the object and given spring constant. Let us see how to start. Right, first of all, see the given data and diagram also see once. So given now spring and cylinder, attaching cylinder to a spring. This is now spring attaching to one cylinder and condition given that half of the cylinder is now in water. So you can see here liquid is now, so water is now to half part is inside. And you can see spring constant given 500 Newton per meter and see what else density. Density given 8000, density of the cylinder or density of body. It is given 8000 kg per meter cube. And see what else given here. Outer diameter is 10 centimeter. That means radius equal to radius is 5 centimeter and a height equal to 20 centimeter. Height is 20. So first we have to find elongation in equilibrium and next time period of oscillations. Let's see how to start. So first condition, it is a floating. So cylinder is a floating means net force must be equal to 0. And you can see density of the body is now 8000 kg per meter. Means density of the body is more than that of water. Okay. That means weight is dominating when compared to buoyancy force. That means spring is having elongation. So if you draw a free body diagram for cylinder, buoyancy force supports. So here weight is dominating. Okay. So it is elongation. Since it is elongation, spring force that will be upwards and weight mg downwards. So now net force equal to 0. Okay. So net force is 0. Then see what we can write. Buoyancy force plus spring force is equal to mg. So in the place of buoyancy force, I can write pi r square into h. This is volume by 2 because it is given half of the volume is inside. Okay. So that's a half of the volume into density of water, that is 1000, right? Into G. So V rho G. This is now buoyancy force. Buoyancy force plus spring force Kx and K value 500 plus kx 500x. Sum of these two forces are balancing weight of the cylinder, that is mg. Mg means I have to take volume pi r square h volume into density. Density is now 8,000 volume into density, that is mass into g. Okay. So remain just a calculation part. So R value is given, H value is given, right? That means this value is known, right? And this value also known, getting it. Now simplifying this, we are going to get the value of x, and that is approximately 23.5 centimeter. Okay, because this value is known and this value also known. Only x is unknown. So simplifying. So making the calculation, right? Okay. Now focus. They're asking like, if you slightly depress it, means press it down and leave it. Then see what is now time period of oscillations. Okay. So here it is in equilibrium. So net force equal to 0. So now what they are doing is, say carefully, it is in equilibrium, net force 0. Let us now slightly press it down. Let us say this goes down by a distance y. Okay, slightly push it down by a distance y. So when you push it down, now having extra volume in the liquid. Okay, since having extra volume, we get extra buoyancy force. See carefully, or let us take this C is x naught. Okay, this is x naught equilibrium. So buoyancy force kx naught, and this is now mg constant. Okay, now see here what changes. Since we are having extra volume inside, we get extra buoyancy force and extra spring force, and sum of those two will become the restoring force. So I'm writing a restoring force, that is equal to k into y. This is extra spring force plus extra buoyancy force, that is pi r square, that is area into y. This is extra volume. See carefully. Pi r square into y. This is extra volume inside liquid. Corresponding to extra volume, we get extra buoyancy force. So into density of water into G. See carefully. Initially, it was in equilibrium. Now, when you press it down, because of extra volume in liquid, getting extra buoyancy force. Next, when you press it down, spring is having extra elongation, that is Y. Extra spring force, extra buoyancy force. This is now net force, which is restoring force. And you can see when you press it down, extra buoyancy force upwards, extra spring force also upwards. So if you want write in vector form, F equal to minus K plus pi r square density of water into G into Y. This minus Y, sorry, minus Y means if Y is a displacement, displacement is down, okay? But force is upwards. That's why taking a negative sign. So this is of the form minus something into Y, okay? So in the place of K, now we're having this expression, right? So time period of oscillations T equal to 2 pi root m by, let me take this as minus some k dash into y. Okay. So 2 pi root m by k dash. Okay. So in the place of k dash, now taking this expression. Now in this k value given, r value given, density of water is known. Now we have to make simplification. Okay. And after making simplification, you are going to get approximately 0.93 second. Right? So I hope you can make calculation part here. Let us see the next problem. A wooden block of mass 0.5 kg and density 800 kg per meter cube is fastened to the free end of a vertical spring of spring constant 15 Newton per meter fixed at the bottom. If the entire system is completely immersed in water, find the elongation or compression of the spring in equilibrium. The time period of vertical oscillations of the block when it is slightly depressed and released. It's almost same as the previous problem. The only slightly changes you can see. First of all, let us make a diagram to get clarity. So coming to diagram, so this is a block which is attached to a spring which is vertical. Spring is now connecting at the bottom. Okay. And we can see now this is a vessel. This system is now completely inside water. That is now condition given. This is completely inside water, right? Now we can focus. First of all, focus the density of the body given. Okay. You can see density of the body 800 kg per meter. That means its density is less than that of water. That means buoyancy force dominates. Okay. So let me make FBD here. If you take FBD, so we got a clarity that density of body is less than that of water. That means buoyancy force is dominating. Buoyancy force is dominate. Force of buoyancy upwards. Since buoyancy force dominating, spring is having elongation. Elongation. So here spring force downwards. Suppose elongation x naught plus mg again downwards. That means now in equilibrium, in equilibrium, sum of the spring force and gravitational force balances buoyancy force. Okay. So first condition is now buoyancy force is balanced by spring force plus gravitational force. Okay. Let us see once the value of spring constant K, that is given 50 Newton per meter, and see what that's density. Mass given, mass that is a half kg, right? That is not a data. Okay. Now see calculation part. So coming to here, substitute values. Kx naught is equal to, first of all, buoyancy force. See buoyancy force how much? Buoyancy force is now buoyancy force volume. Volume means I can write mass by density. Okay. That gives volume into density of water into G. Okay. So substitute values are mass 0.5 upon 800. This gives us volume into density of water 1000 V rho G, G value 10, that is buoyancy force, minus mg. Mg it is 5. Okay. Now see how much we get. This is, we can see two zeros and here 2. Remaining this is 5. This is 50. 50 by 8. 50 by 8 means 6.25. 6.25 minus 5, that is 1.25. Okay. That means x value or x naught, that is equal to 1.25 upon 50. Okay. This is meter. If you want in centimeter, into 100, right? So 1.25 upon 50 into 100, that is in centimeter. Okay. That is how much? 2 times 2 into 1.25. That is 2.5 centimeter. It's almost same as the previous one. And coming to time period, T equal to, directly you can write, if you slightly see from equilibrium position, if you slightly push it down, if you slightly push it down, see what happens, where change comes. There is no change in buoyancy force because volume is a completely inside. No change in buoyancy force. This remains the same. Mg also remains the same. Okay. That means now the only change is, it is spring force. That means here no change in buoyancy force, no change in gravitational force. Therefore, time period is only because of spring force. That's why 2 pi root m by k. Okay. It is 2 pi root m by k. Now substitute values in that. 2 pi root m value half, and k value 50. That means how much you get? 2 pi 100, that is 10. It is a pi by 5 per second. So you should be very careful. In the previous one, what happened? If you observe carefully, only some part of the volume was inside liquid. Okay, that's why buoyancy force also changing there. But coming to here, entire volume is inside. That's why no change in volume, no change in buoyancy force. Only change is now extra spring force, which provides restoring force. That's why simply 2 pi root m by k, right? Let us see the next problem. Let's see the question given. A cube of ice of each 4 centimeter is placed in an empty cylindrical glass of inner diameter 6 centimeter. Assume that the ice melts uniformly from each side so that it always retains its cubical shape. Remembering that ice is slightly light, ice is lighter than water. Find the length of the edge of the ice cube at the instant it just leaves the contact with the bottom of the glass. Okay. So here actually they have to mention density of ice, that is 0.9 gram per cc. Let us see first of all the given data. Right. First focus the question given, the data given. A cube of ice of H. So take it as A, that is given 4 centimeter. Placed in an empty cylindrical glass of inner diameter 6 centimeter. That means radius equal to 3 centimeter. Okay. Right. And density of ice we are taking as 0.9. Okay, gram per cc. Now see what happens. This is now cylinder. Now having ice, it is a cubical block of ice. Ice. This is ice block. Now it is given that ice is melting in all directions uniformly so that it maintains its cubical shape. Now what happens is, he is asking what is the size, or you can say the side length of the ice block when it is just leaving the contact. You can see density is 0.9 and density of water, that is 1 gram per cis. That means ice block losing contact when it is 90% of its volume is inside water. That is our key point to start the problem. Let us see now. When it is losing contact, when it is losing contact with bottom, 90% of its volume will be inside water. So we have learned that whenever a body floating, volume inside upon total volume is equal to density of the body upon density of liquid. Here body is now ice, 0.9. Liquid is water, it is 1. So 90% of the volume will be inside of liquid, okay? Let me take side length equal to x. Then this will be equal to 0.9x. I'm taking x is now side length of ice. Then 0.9x will be inside water. Then just losing contact. Okay. Now see key point to start this problem. So here, since ice is melting and converting into water, volume is not a constant because density of ice and that of water both are not same. But mass will be constant. So I'm equating here mass. Okay. No change in mass. So mass of ice, volume 4 cube into density. Density of ice 0.9. This is mass of ice. That is equal to when, if you see volume of ice, x cube side length into 0.9. This is volume of ice. Now see carefully. I want to calculate only this part of the volume. Okay. Then what we have to do is first find out volume of this part of cylinder. Okay. Find volume of this part of cylinder. From this volume, subtract volume of this part of the ice. That gives volume of water. I am repeating. First calculate volume of this part of cylinder. From that volume, subtract volume of this part of ice. That gives volume of water. Okay. Then see here what I'm writing. Pi r square into 0.9x. That gives volume of cylinder. From this volume, subtract volume of ice, this part of ice, that is x square into 0.9x. Okay. So if this is a clear, remaining just a calculation part. Okay. You can see 0.9x cube, 0.9x cube. These two are cancelled. Remaining only 4 cube into 0.9, that is equal to 4 cube into 0.9, that is equal to pi r square 3 square into 0.9x. 0.9 cancelled. X equal to, it is directly simple calculation, right? So making calculation, we are going to get 2.26 centimeter. So here key point is that one is 90% of the volume of ice will be in water at the time of losing contact. Second key point, mass. Mass is a constant. Volume is not constant. Okay. So I hope you got a clarity.